Today we'll be talking a little more about probability. We'll be talking about sample space and counting outcomes. So first we need some definitions, as we usually do. So an event is like an experiment. So it's I'm going to say an experiment, and then that's like an action or a trial, like you're just doing something, trying it out, and it has varying results. With varying results. Okay, for example, let's say you could roll a die. So an example is rolling a die. You know, that's singular for dice. And seeing what you get. Your possibilities are you could land on a 1, a 2, a 3, a 4, a 5, or a 6. Those are your possibilities, which would be your outcome. So an outcome is a possible result from the experiment. So if you rolled the die, you've got 6 choices. So let's say you rolled the die, that's your event or your experiment, and your outcome was a 3. Let's say we landed on a 3. But your sample space, remember we talked about sets yesterday and what was in a set. Sample space is the set of all possible outcomes. The set of all possible outcomes. So remember, we list them in these braces, and I already said the options were to land on a 1, 2, 3, 4, 5, or 6. That's your sample space. That's your set of all possible outcomes. Then probability. That's what this whole unit is about. The probability of an event is a number from 0 to 1. The probability of an event is a number from 0 to 1 that describes how likely it is that an event will occur. Those closer to 0 are less likely to occur, and closer to 1 are more likely to occur. So the probability of the probability of an event happening is a number from 0 to 1. So closer to 0, less likely, closer to 1, or more likely. Now, in the rolling the die example, every number has the same likelihood of happening. But we're going to look more at this probability tomorrow and how it applies. Today we're going to look at it with tree diagrams. A tree diagram is a useful way of finding the sample space when there are multiple actions. So like you rolled a die, then you tossed a coin, or you did multiple things, kind of a series. Draw a tree diagram, then list the sample space and determine the number of outcomes. All right, this is how a tree diagram works. Picking a digit 1 to 8, then tossing a coin. So picking a digit 1 to 8, let's list our possibilities. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 possibilities. For every one, these are like here's my tree, and here's my first branches on the tree. And then for every one of these, they have branches. If you picked a 1, then tossed a coin, your possibilities are a 1, then heads, or a 1, then tails. So for each of these, after you picked the number, you could get a heads or a tails. This is your tree. This is what I mean by a tree diagram. So for each of these, let's list our sample space. This might take a while. Your sample space is all the possible outcomes. So what do we have? We have a 1 in heads, a 1 in tails, a 2 in heads, a 2 in tails, a 3 in heads, a 3 in tails, a 4 in heads, a 4 then tails, 5 then heads, 5 then tails, 6 heads, 6 tails, 7 heads. Told you this would take a while. 7 tails, 8 heads, 8 tails. Oh, how many total outcomes is that? Well, we could sit here and count them all. 16. But can't we use some logic? Sorry, I just realized that wasn't in the picture. We could use some logic to see 8, and each has 2. 8 times 2 is 16. All right, what's the probability of randomly guessing the answers, because I know some of you do this, to the last 3 multiple choice questions of a test if there are 4 options for each question? So randomly guessing the answers. Okay, so I've got 1 question, 2 questions, 3 questions. Each question has 4 options, an A, B, C, or D. A, B, C, D. A, B, C, D. Now this one's a little confusing to me. Probably should have changed the wording. It depends on if we're saying what's the probability of you getting all 3 of them right. That gets a little more complicated. So let's just talk about our sample space of what we could guess, because we're not, I guess we're talking about possible guesses, not whether or not you're going to get them right. We'll talk about that on a different question in this unit. So you could pick 1A, 1B, 1C, 1D, then you could pick 2A, 2B, 2C, 2D, then you could pick 3A, 3B, 3C, 3D. Those are the possibilities. So the number of outcomes is 12. You can count them, or you can think 3 times 4. Let's look at one more with a tree diagram. Choosing a day of the week, then choosing a letter from the word math. Okay, hopefully you know your days of the week. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. I don't remember where I learned that. Anyway, there's your days of the week. And then choose a letter from the word math. M-A-T-H. M-A. This is going to take a while, isn't it? So maybe let's pretend I did this. So you've got, because I think we catch on by now, and we can see that our sample space is going to be, how do I do this? Sunday M. Maybe I should have put a 1, 2, 3, 4, 5, 6, 7. Anyway, you get the point. So 7 days of the week, 4 letters in math, there's 28 outcomes. All right, now, how clunky and time-consuming is that to make a tree diagram, write all that out, count them? So why don't we just use a rule, the fundamental counting principle. If one activity can occur in M ways and another activity can occur in N ways, then both activities can occur in M times N ways. Isn't that what we did up here? We multiplied 7 times 4. We multiplied on the previous page. So we can just multiply. All right, let's look over here at some examples. Choosing a month of the year and a single digit from 0 to 9. Okay, what do I have? 12 months of the year. How many digits are there from 0 to 9? I know your brain probably wants to say there's 9, but you got to count 0. So there's 10. So how many outcomes? 120. Okay, choosing a letter of the alphabet, then tossing a coin. In case you're not sure, there's 26 letters of the alphabet. And how many choices when you toss a coin? 2, right? Heads or tails? So that's 52 outcomes. Okay, choosing a pair of pants, a shirt, and a belt from 3 pairs of pants, 5 shirts, and 2 belts. Now it works for 3 different choices. If you have 3 different events or possibilities, you still just multiply them all. Rolling a standard die 4 times. All right, we already said there's 6 choices. Don't do 6 times 4. You're rolling it 4 times, so you can get 6 choices, or 6 choices, or 6 choices, or 6 choices. 1,296 choices. That's a lot. Creating a 4-digit password from the digits 0 through 9. Now don't get confused here. If you want a 4-digit password, you could pick first digit. You have 10 choices. Second digit, 10 choices. Third digit, 10 choices. Fourth digit, 10 choices. That's 10,000 options. And that's just with digits 0 through 9. So imagine how many options there are for passwords if you throw in letters and symbols and capitals and all that. All right, spinning the spinner to the left. I got to look at that 3 times. Okay. No numbers are repeated. There's 16. I'm going to spin it again. There's still 16 choices. Spin it again. There's still 16 choices. 4,096 choices. And then now we're going to toss a coin 5 times. So we have heads or tails, heads or tails, heads or tails, heads or tails, heads or tails. We have 32 choices. So this lesson was about figuring out how many possibilities there are, your sample space. And tomorrow we'll look a little more at 2 different kinds of probability.